Degrees and radians are two ways to measure angles. To switch from degrees to radians, just multiply your angle by pi divided by 180. Let's try 240 degrees. Multiplying by pi over 180 gives us 240 pi over 180. Simplifying the fraction, we get 4 pi over 3. Now for 15 degrees. 15 pi over 180 simplifies to pi over 12. Remember, always simplify your fraction at the end to keep things clean. Negative angles work just like positive ones. We multiply by pi over 180 degrees. For minus 60 degrees, we get minus 60 pi over 180, which simplifies to minus pi over 3. Let's try minus 225 degrees. We keep the negative sign constant. Multiplying gives us minus 225 pi over 180. Simplifying the fraction by dividing by 45, we arrive at minus 5 pi over 4. Today, we learn the Euclidean algorithm to find the greatest common divisor, or GCD. Instead of listing factors, we use division to shrink the numbers until we find our answer. The core idea is simple. The GCD of two numbers is the same as the GCD of the smaller number, and the remainder from dividing the larger by the smaller. Let's find the GCD of 75 and 10. We divide 75 by 10, which gives us a quotient of 7 and a remainder of 5. Now we apply the algorithm again. We take 10 and the remainder 5. Dividing 10 by 5 leaves a remainder of 0. When we hit 0, the last non-zero remainder is our GCD. So the GCD of 75 and 10 is 5. Let's find the greatest common divisor of 180 and 40. We start by dividing 180 by 40. Now we divide the previous divisor 40 by the remainder 20. Since the remainder is now 0, the divisor 20 is our greatest common divisor. Next, let's look at 125 and 25. The remainder is already 0. That means the divisor 25 is our GCD. Finally, let's solve for 90 and 20. We continue with the next step. Divide 20 by 10. The remainder is 0, so the GCD is 10. These examples show how the Euclidean algorithm reliably leads us to the answer. Working with larger numbers is simple when we use the Euclidean algorithm. Let's find the greatest common divisor of 305 and 50. We divide 305 by 50 to get 6 with a remainder of 5. Then we take our previous divisor and divide by the remainder. Since 50 divided by 5 leaves a remainder of 0, our last non-zero remainder, 5, is the GCD. Now let's try 11204 and 400. 1204 divided by 400 is 3 with a remainder of 4. We divide 400 by 4, which gives us 100 with a remainder of 0. That makes 4 our greatest common divisor. When one of the numbers is prime, the Euclidean algorithm behaves quite predictably. Let's look at 29, which is a prime number. Consider 29 and 58. Because 29 divides 58 perfectly, the remainder is 0 immediately. The greatest common divisor is 29. What if we use 29 and 57? 57 divided by 29 leaves a remainder of 28. Then 29 divided by 28 leaves a remainder of 1. Since we reached 1, the numbers are coprime and their GCD is 1. Prime numbers simplify our steps because they usually lead us to a remainder of 1 very quickly. Let's look at our final examples. First, find the greatest common divisor of 29 and 59. Since both numbers are prime, they share no divisors other than 1. Next, calculate the GCD of 29 and 60. We use the Euclidean algorithm. 60 divided by 29 leaves a remainder of 2. Then, 29 divided by 2 leaves a remainder of 1. Because the remainder is 1, the GCD is 1. Remember, if a prime number doesn't divide the other number, their greatest common divisor is usually 1. Great work on these exercises.